When two atoms are far apart, they can really be described by atomic quantum states and independent of one another. But as they move closer together, the Coulomb forces between them begin to become important. So let's think about how this works for example, two hydrogen atoms coming together, since that's our prototypical bonding system. All right, so I have one hydrogen atom over here and another hydrogen atom over here, and each of them is in a quantum state that actually is an atomic quantum state, but they're going to move closer together. And as they do, the electron on this hydrogen begins to feel the proton on this hydrogen, and vice versa. And that's what I mean by interacting atoms. They get so close together that they begin to exert Coulomb forces on one another. And so it becomes more and more difficult to treat them as an independent entity, and they become, in essence, a molecule. Well, it turns out that there's two different predominant approaches for talking about the wave functions of this system as they come together. Now, I'm going to present to you the first method historically, although it is not the one that is more commonly used today. Okay, back in the 1920s, Heitler and London got together and they said, well, when I have two states like this, if I consider the electron on this molecule or on this atom to be electron 1 and the one on this electron to be electron 2, then I might be able to write these wave functions as follows. I could write that the total wave function is simply the product of the two wave functions. So I'll call this 1sa, so that's the 1s orbital on hydrogen A holding the first electron. And on this case, I'll have 1s of B holding that electron. Okay, so this would be a perfectly fine way to write this wave function when we have separated atoms. In other words, the total wave function of the system when they're very far apart probably looks something like this. All right, but as they become closer together, then you might say, well, you can't really just definitively say that electron 2 is on hydrogen B and electron 1 is on hydrogen A. We have to add a term that allows for them to be on the other atom. And in particular, if I were to bring these two together and form a bond and then pull them apart again, who's to say that electron 2 won't end up on atom A and electron 1 on atom B? So this gives us a fuller picture, at least, of the full wave function that allows for the indistinguishability of the electrons. All right, this particular formulation is something called the valence bond formulation. And the valence bond theory, and I mentioned their names very quickly, but was used by Heitler in London in what ended up being the very first successful description of bonding using quantum mechanics. All right, and it's a perfectly fine way to go about it. However, let me point out one thing. If I were to pull a normal hydrogen molecule apart, sure, I'll get more than likely two atoms out of it, but I could also get two ions. I could also end up getting H minus and H plus. There is some small probability of getting that. But the Heitler-London valence bond theory doesn't really get us there. We don't have any possibility of a wave function that has both of the electrons on one of the atoms and none of the electrons on the other. So in this sense, it is a limited picture of what's going on in these atoms. Now there's another way we can proceed, and that is by taking sort of a more holistic view of the entity of H2 as a molecule. And when we do this, we would now maybe start with thinking of the two protons that are within bonding distance of one another, and so they obviously have a repulsion here from their separation, but they also have an attraction. And so now let's suppose we start with those two protons and somehow we have managed to bring them close together, and now we're just going to toss electrons in one at a time. Well, we toss one electron in, it's going to feel the Coulomb force for both of these protons, and so it's going to inhabit a region that, for example, would lay all around those protons. So a better way to write the wave function in this particular case would be, for example, to write the wave function as 1sa1 plus 1sb1. In other words, it's partially on each of these. Now, if I were to add a second electron, I would put it in this same orbital. So it would be 1sa2 plus 1sb2. So this is clearly where the electron 1 is. This is clearly where electron 2 is. And so the two of them are occupying a similar orbital. We now know from doing our studies of multi-electron atoms that, for example, the Pauli exclusion principle may hold sway here, and we'll see that a little bit later in this module. But in essence, what we're saying is that both of these electrons are inhabiting the same region of space, and they're the things that are forming this bond. And this is, in fact, one way that we can think of a covalent bond being formed, because the two electrons are both being shared between the two atoms. So this, if you will, is sort of an early way of thinking of covalent bonding. Now, this particular approach, if we expanded all this out, we would have terms that include both the terms here that represent splitting this thing into two atoms, but we would also have terms that would include ionic terms. So this allows for ionic separation. But in fact, because of the way it's constructed, it overemphasizes the ionic separation. So it also has some weaknesses in this that overemphasize certain outcomes that, in fact, may not happen. This particular approach is called the molecular orbital theory. And this was one that was largely developed in the 1930s by Robert Mulliken. And it is the one that is, I'll say, the predominant approach that is used today in describing the electronic structure of molecules. Okay, these two entities that we've drawn here are essentially what we're calling molecular orbitals. And we'll have a lot more to say about molecular orbitals, but it turns out that this approach, because of the way it is put together, is in fact a better one to use when we're talking about H2+, which is going to be our focus for much of this lesson and following. All right, so as we talk about H2+, we're going to write the wave function for H2+ as follows. We're going to say the wave function, and there's only one electron, so I don't have to worry about giving it labels like 1 and 2 here, but we'll simply write it as the sum or the difference of two atomic orbitals. Now I'm using a little bit different notation here because I intentionally want to be a little bit more general. We're going to come back and revisit these results for a particular 1s orbital many times, but I want you to just think of phi A and phi B as being atomic orbitals, and their subscript labels the atom or the proton around which they are formed. Okay, so the overall electronic wave function is going to be some kind of linear combination of these two atomic orbitals. Well, of course, we have a name for that. We call this the linear combination of atomic orbitals. And instead of writing all that out every time, we just abbreviate it LCAO. Linear combination of atomic orbitals. Now, moreover, this forms what we call a molecular orbital, so we might call this, in essence, a simple example of an LCAO-MO. All right, you're going to hear a lot of acronyms. I apologize for that. I'll try to describe what those acronyms mean as we go along, but this is the first one that we've encountered. All right, now let's see what this looks like if we're talking about, for example, two hydrogen atoms coming together so that their electrons are in atomic orbitals that are 1s orbitals. So in other words, if both of these were 1s, what would all this look like? All right, so let me draw some pictures. Okay, we know from our study of the hydrogen atom that the 1s orbital for the hydrogen atom looks something like this, and I'm going to try to draw it very carefully. It's basically an exponential decay. Okay, so the 1s orbital is one that has a normalization constant, and I'll use the NLM labels on this. And the functional part is really just e to the minus r over a0. Okay, so this is r and this is psi. Okay, so it's just an exponential decay. So when we bring two of these together, this is where we end up having to get a little bit tricky in how we do this. So what I'm going to do is draw a line which represents sort of the r-axis and the positions of the two nuclei along that line. And to fill out my diagram here, I'm going to draw a little line down here just so that I have a marker that tells me where these nuclei sit in horizontal space. Now, for this nucleus, I'm going to have an exponential decay that comes down like this. And for this, I'm going to have an exponential decay as well. But since I'm really talking about plus or minus distance, r is not really the relevant coordinate here. It's the coordinate that connects the two nuclei. So this is going to come down an exponential decay on both sides. Okay, the distance from this representing r. All right, same thing over here for this second nucleus. I'm going to have exponential decays that come in both directions. And I'm sorry I'm not drawing this very well. So when I add these things together, so for example the plus combination, what will it look like? Well, in this case, over here, this one is very small, so it's really going to be right on top of this curve, and it begins to grow as I get closer to the second one. And likewise over here, it'll be very close to the second curve. But you'll see in the red drawing, that's where we have sort of a picture of the electron density, if you will, when we bring these things together to make this LCAO-MO. All right, so you'll see a lot of pictures like this. I'll tell you personally, I'm bothered by the fact that there are little pointy tops here on these wave functions, but it is, in a certain way of thinking, it is an accurate way of thinking where the electron is. But there are going to be other factors that influence these electrons. They cannot, in fact, be right on top of the proton, so we'll deal with that later, I suppose, when we get to it. But I want you to have this picture in your head that when we're creating a molecular orbital, it's basically a space over which the electron is spread across both of the protons. So if you want, you can think of this as a delocalized version of an atomic orbital. Now it just happens to have two atoms.